I'd like to conclude this first lecture on recursion by talking about pure recursive functions. A pure function is like a function in math. It is a function that returns a value and it doesn't do anything else. Doesn't update any non-local variables, doesn't talk on the network, doesn't do anything like that. It's just a function. And pure functions are like functions in math. If you call them with the same arguments, they always give you the same result. And that's really a nice property. So in order to understand the execution of a pure function, you can do it by looking at the base case and then working back up. So what I showed you before was how to write a recursive function. Now what I want to tell you is how to read a recursive function. So if I have a function such as this one, we can try and figure out what it does. So let's look at first, we need to figure out where the base case is. So the base case here, if n is 0, return 1, and there's in, that's the parameter. And you can see, oh, the recursive call is for in minus 1. So as long as we start with a positive number, we'll keep going down until we hit something 0 or negative and stop. Okay, so the base cases here are all going to be any negative number or 0. So let's just pick 0. And you can see that if I hit 0, then the return value is immediately 1. Straightforward. Okay, so we can make a little table here. F of 0 is 1. All right, what about f of 1? Well, if I think about f of 1, what's going to happen? Well, 1 is not less than or equal to 0. So instead of returning, we're going to compute f of n minus 1, and we're going to return n times f of n minus 1. So, all right, so what is n in this case? I called f of 1. So n is 1. And what's f of n minus 1? Well, that's f of 0. Okay, fortunately, I just computed f of 0, and that's 1. So that's 1 times 1, that's 1. Let's do it again. So f of 2, what's that going to be? Well, applying the same sort of reasoning, it's 2 times f of 1. Okay, again, we just computed f of 1, so that's 2. F of 3 is going to be 3 times f of 2. And we just computed f of 2, so that's 2. So 3 times 2 is 6. F of 4 is 4 times f of 3, so that's 4 times 6, 24. Ah, this is the factorial function. Yay. Okay, that's just fine. This is an easier way to understand recursive functions than the other way, which is, let's say I ask you, what's f of 3? All right, you might try to say, well, f of 3 is what, 2 times f of 2. Then you have to figure out, well, what's f of 2? F of 2 is 2 times f of 1. What's f of 1? That's 1 times f of 0. And what's f of 0? Well, there you finally get the base case 1. And now you can perform the multiplication. So 1 times 1 is 1, 2 times 1 is 2, and 3 times 2 is 6. Okay, so that'll tell you we get 6. You can imagine doing this for f of 5 or f of 17. It starts to get a bit longer. The nice thing about this reasoning is that if you start at the bottom, everything works very neatly. It builds up as a table. Let's look at one other example. This is a function g that takes parameter n. At the base case, it returns in. And for the inductive case, what is it doing? This is a bit more complex. So we have 2 calls to g, and they have different parameters. And then the results of those are added together for the result. So let's just start at the bottom and work our way up. What does this do for 0? It returns 0. What does it do for 1? It returns 1. Okay, and for any negative number, it would just return the negative number. Okay, what about for 2? 2 is the first non-trivial case here. For 2, this is going to call g on 1 and g on 0. So, and what we're going to do is add g on 1 and g on 0. And we're going to get the sum of those. So we happen to have just computed g of 1 and g of 0. So there they are. When we add them together, we get the result 1. So, okay, that's g of 2. What about g of 3? Well, that'll be computed using g of 2 and g of 1. So if we add g of 2 and g of 1 together, well, what were those? We've just computed them, so that's handy. We have a table. What we're doing is building up a table. So 1 and 1 is 2. Likewise, for g of 4, we add the previous 2. So for g of 4, we're adding 1 and 2. For g of 5, we're adding 2 and 3. For g of 6, we're adding 3 and 5. For g of 7, we're adding 5 and 8. For g of 8, we're adding 8 and 13, etc. This is the Fibonacci sequence we're computing. And the Fibonacci numbers get quite large quite quickly. I'm going to claim that understanding this Fibonacci function, it's a little bit more complicated than the factorial, but it wasn't that bad. And why wasn't it that bad? It's not that bad because we started at the base case and we sort of built everything up. In the case of the Fibonacci function, if you start at the top and try and reason about what's going on, you end up with something kind of horrible. So in particular, let's think of like g of 5. Well, that's g of 3 plus g of 4. What's g of 3? Well, that's g of 2 plus g of 1. Well, what's g of 2? That's g of 0 plus g of 1. So to get to a base case here, you've got to do quite a lot, all right? But then g of 4, of course, has to be g of 3 plus g of 2. So note that in computing this, I'm going to compute g of 3 all over again in order to, get g of 5. This is quite dreadful, and you can see the call tree here is quite terrible. So when I call g of 5, that calls 4 and 3, but then 4 calls 3 and 2 again. And so you can see the number of calls to g of 1 is in general going to be very large here. And this is not fantastic. So the way to think about this is that we're violating some rules. So let's think about what the rules are for looping and for recursive functions. They're very similar, but we have one extra rule for recursive functions. All right, when we're looping, we have an index variable. We have to start somewhere that's valid, say 0. We have to find a base case, tell us where to stop, say the end of the list. And we need an inductive case to get us closer. Say we just go incrementing by 1. All right, what are the rules for recursion? They're the same. Yeah, we have to have some index that tells us where we are. We have to start in a reasonable place. We have to find some place to stop. That's our base case. And we need some way to get closer to that base case. The one thing we can do in a recursive function that we can't do in a loop is we can actually have the inductive case do overlapping work, because we can do multiple calls in a recursive function. In a loop, you can only go forward once. In a recursive function, as we just did with Fibonacci, you could go forward more than once. This is a very bad thing. And what we're saying here is that the inductive cases in this version of the Fibonacci function are overlapping. So the problem here is that g of 5 computes g of 3 twice, and that's a problem. So my two calls are overlapping. So we need to make sure that we don't do overlapping work in a recursive function, or we'll end up with an exponential explosion of work.